So in last class, we talked about the spherical wrist. And spherical wrist is when you have three revolute joints that are mutually perpendicular to each other. In last class, we also talked about if you have a spherical wrist, you can face the problem of gimbal lock when the second revolution in the sequence goes to 90 degrees. The first and the third revolution, they represent the same degree of freedom. That means you have a gimbal lock. Even though you have a three revolute joints, out of those three revolute joints, two revolute joints do the exact same thing, which means 1 degree of freedom is gone. Now, we also talked about the velocity analysis, and I kind of wrote the equation for velocity analysis. In today's class, I will spend some more time in talking about it in detail. But if you look at the code is first you have H01, H12, and H23 that we multiplied all together. And then we solved the forward kinematics problem and the inverse kinematics problem. Are you with me so far? And at the end, we got the Px, which is the x displacement of the end effector, Py, which is the y displacement of the end effector, and Pz, which is the displacement in z direction of the end effector. I just want you to understand very clearly that all these displacements are vectors. They need an origin. So all these displacements start from the fixed or the zeroth frame, which is the inertial frame. And when we find out the velocities, Vx, Vy, and Vz, those are inertial velocities. Because please try to understand, unless you measure the velocity with respect to fixed frame, you are not gonna get an absolute value of velocity because the intermediate frames are moving. So if you are in a train walking at 3 miles an hour and the train is going in at 10 miles an hour, for you, it may seem like you are going at 3 miles an hour, but for a stationary observer, your actual velocity is 10 plus 3, 13 miles an hour. That is the inertial velocity, and that's what we need to find. When we perform the inverse kinematics, please try to understand, I did not specifically mention this, that this inverse kinematics was only performed on positions, which means if you look at the way the inverse kinematics solution is computed, we gave MATLAB the values for Px, value for Py, value for Pz, and we equated that to a symbolic expression that contains θ1, θ2, and θ3. And then MATLAB solved that expression and gave us the value of θ1, θ2, and θ3. Do you agree with me? Now, this is what we did for inverse kinematics to find joint angles. Now, let me take this problem and try to sort of phrase it differently. Imagine in this particular case, if my A1, A2, and A3, those three linked lengths are 0. And what I'm gonna say here is, and this is an important problem. If I say my A1 is 0, my A2 is 0, and my A3 is 0, this is actually a true spherical wrist. Everyone agrees? And what I'm going to do is I'm going to write, or I'm going to find out H0 3, and you will realize that the last column will have zeros, which means my px is equal to 0, my py is equal to 0, and my pz is equal to 0. Do you agree with me? Now what I want to do is I want to solve inverse kinematics problem on the spherical wrist. I'm trying to see my mouse. Okay. I want to solve the inverse kinematics on the spherical wrist. What do I mean by inverse kinematics on spherical wrist? Inverse kinematics on spherical wrist is end effector orientations are given to you. And from the end effector orientations, I want to find out the joint angles. This problem is different than the problem we solved last time. Last time, we assumed non-zero values of A1, A2, A3, and clearly we got non-zero values of Px, Py, and Pz. Those non-zero values got back substituted and gave us the joint values to achieve the desired end effector position. Do you agree with me? I want you to understand, if you use that approach, you cannot have orientation calculated separately, because your theta 1, theta 2, theta 3 for the end effector positions are fixed, which means those theta 1, theta 2, theta 3 needs to go here, and that will dictate the orientation of the end effector. But that is not the purpose of the spherical wrist. Spherical wrist primarily is used for the orientation and not position. Do you agree with me? So the real inverse kinematics problem that most of us will try to solve is, you are given a spherical wrist. Spherical wrist end effector has certain orientation, and that orientation could be defined in terms of Euler angles. It could be defined in terms of quaternions. It could be defined in terms of Euler parameters. It could be given in terms of direction cosine matrices. Doesn't matter. We can convert, we can go from one convention to other convention. But the problem now is, you are given some orientations that end effector needs to achieve. And the question is, what should I set up my theta 1, theta 2, and theta 3 to achieve that orientation? Everyone understood this? Now, if you look at the technique that we have used, just using MATLAB to solve the problem, this will not work. Why? Because if you think about it, this orientation matrix has 3 by 3, so 9 elements. What it means is, essentially, if you want to follow the technique brute force, you have 9 variables. I mean, you have 9 equations, and you have to solve 9, and you have to solve 3 variables. So usually, whenever you have to solve the inverse kinematics problem for spherical wrist, here is the process to do that. The orientation will be defined in terms of Euler angles, roll, pitch, and yaw, quaternions, 4 elements of quaternions, which is the normal vector axis. So axis will be defined, and a constant or the module will be defined, modulus will be defined. Whatever it is, we take that and convert it into this 3 by 3 rotation transformation matrix, and I will solve problems. Not today, in next class, I will solve problem how to solve the inverse kinematics problem for spherical wrist. So the technique here is, you would construct a 3 by 3 matrix from the orientation information that is given to you. Everyone understood this? So they will give you some orientation information. You take that orientation information. It could be direction, cosine, cotonian, Euler parameters, Euler angles, whatever it is, and find a 3 by 3 matrix. That matrix needs to be equated to this 3 by 3 matrix. Everyone understood this? And then the life becomes very simple. Please understand. Third row, third column in here gives me sine T2. So what you will do is you will equate the third row, third column in your resultant solution or the resultant orientation with sine T2. Once you get sine T2, you will find T2 and then get sine T3. Once you get sine T3, you can actually find out cosine T1, which means you can get T1. So what I'm saying here is select the expressions that do not involve multiple variables. So first you can find sine T2, then you can find T3, and then you can find T1. And you don't have to follow the route that I said. You can follow, you can select some other equations and still be able to find out theta 1, theta 2, and theta 3. Everyone understood this? And I will write this down when I actually explain. But I want you to understand that if you have a spherical wrist, Px, Py, Pz's are going to be zeros, and you are only left with the orientation information. So you have this 3 by 3 matrix, and somehow you need to equate this 3 by 3 matrix to the resultant orientation, and then capture or find out the individual values of joint rotation. Everyone understood this? And I will explain this again when I go on to the whiteboard. The next thing which I talked about is finding out the velocities. Now, some of you may ask me, does everyone remember the equation that I wrote in last class for the velocities? And I'm going to use the blackboard. So hopefully my online students can see this. The expression that I wrote was omega x, omega y, omega z. These are the inertial angular velocities. What do I mean by inertial angular velocities? Which means if you have a robot, and I think our robot had these axes, right? Z naught, X naught, Y naught. So omega X is about I naught. Y naught is J naught. And omega Z is K naught. So these are vectors. Omega X is the angular velocity about the x-axis. Notice the thumb is pointing in the same direction as x naught. Omega Y is the angular velocity about y naught axis. Note thumb is pointing the same direction. And K naught is the angular velocity omega Z. So this is omega X, omega Y, and omega Z. Now, this is the inertial angular velocity of the robot end effector described in the fixed frame. This is given as So 0 R1 multiplied by 0 0 theta 1 dot plus 0 R2 multiplied by 0 0 theta 2 dot and plus 0 R3 multiplied by 0 0 theta 3 dot. Now this needs a little discussion, and what I will do is, the reason I wrote on the whiteboard is because I want to show you directly onto the MATLAB script that how you can find this. You don't have to redo the calculations or repeat. So I want you to understand what is the physical interpretation of 0 R1. 1 means, this is very important, there is omega x I1 J1 K1. This is I2 J2 K2. And this is I3 J3 K3. And if you look at the sign convention that we have used so far, all our rotations were about the z-axis of that individual joint. So I1, J1, and K1 are the unit vectors for the frame 1. I2, J2, K2 are the unit vectors for frame 2. And I3, J3, K3 are the unit vectors for frame 3. So this entire transformation is nothing but the angular velocity about the K1 frame or K1 got transformed to the inertial frame. Angular velocity in frame 2 got transformed to the inertial frame. Angular velocity in frame 3 got transformed into the frame 0. Everyone understood this? And it is very important to understand that I have added these three together. Okay. And this is based on a very important assumptions that when I'm performing these summations, the changes in theta 1 dot, theta 2 dot, theta 3 dot, and remember this is going to include theta 1. This is going to include theta 1 and theta 2. And this is going to include theta 1, theta 2, and theta 3. These are all small quantities. If these are small quantities, only then this addition makes sense. And that is the basic assumption for infinitesimal rotation. These rotations are assumed to be very small, which means at that time step, the variation between the previous value and the next value is small enough. Very important. Is small enough so that cosine terms can be approximated at 1 and sine terms can be approximated at the angle itself. If you violate that assumption, you can't just linearly add these rotations together. So that is what is the meaning of. Now what I want to do is, how would we do something like this, or how do we find angular velocities with the MATLAB code that we have already written? Please understand all the elements of 0R1, 0R2, and 0R3 you have. So what I want to do is, I want to show you that if I were to find out the angular velocities how can we do it? So please understand H01 is already known. So in H01, the first 3 by 3 matrix is 0R1. Do you agree with me? Yeah. Then H12, what you will do is you will multiply 0H1 multiplied by H12 and you will get one more matrix. And then finally, you would have the last matrix that you already have calculated. So here, one step you want to add, which we did not do earlier, is H02 is equal to H01 multiplied by H12. And once you have this, so what you have, you just click here. And now you have all these matrices that you need to perform your manipulation. So you already have first 3 by 3 matrix of H01, which will go here. First 3 by 3 matrix of 0H2 that will go here, and the 3 by 3 matrix of 0H3 that will go here, and then you'll just multiply with these guys. Are you with me so far? I will work out a problem, but I wanted to show you that whatever we did actually follows very well to the velocity analysis. And these velocities, whether they are translational velocities or rotational velocities, they must be in inertial coordinate frame. They must be with respect to the fixed coordinate frame. You are not studying theory of relativity. We are actually looking at an absolute velocity, absolute rotations, and everything absolute. Any questions? Yeah.
Why are these called inertial?
Inertial. What is the meaning of inertia? Inertia means lazy, like me. So I am very lazy. So that's why this frame is called inertial. It's very lazy. It cannot be moved. That's why these are called inertial velocities. Velocities that are defined with respect to inertial frame.
The frame that does not have any velocity.
Yeah, the frame that is fixed. That's why the frame that is fixed. That is inertial frame. And Newton's laws are valid in inertial frames. So, any other question? Okay, now what I'm gonna do is, I am gonna go to the whiteboard, and then quickly give you the overview of what we discussed. And then we can solve the next problem. But when we solve the next problem, what I want to do is I want to actually solve the problem from scratch. Okay. Okay. So quick recap for a spherical wrist. We are talking about spherical wrist. Inverse kinematics. So the joint rotations, so end effector rotations, can be expressed as a direction cosine matrix It could be expressed as roll pitch yaw. It could be expressed as Euler angles, which is or Euler parameters. There is something called as Rodriguez parameters. It could be expressed as quaternions, or it could be expressed as rotation matrices. And every approach has its advantage and disadvantage. So what we will do is, no matter how the end effector orientation is defined, no matter how the end effector orientation is defined, we will use MATLAB or some other mathematical equation to find out the rotation matrices. So this rotation matrix will be a fully populated matrix with 9 terms. And some of these terms would be 0. But at the end of the day, this rotation matrix will be fully populated matrix. So I give an example. So I may say that 20-degree roll, 30-degree pitch, 40-degree yaw. So you can use the MATLAB command Euler to rot, and that will convert these Euler angles to a rotation matrix, and that will be a 3x3 rotation matrix. And now, a minute ago, I gave you the expression for the rotation matrix. And to be honest with you, I don't remember the entire rotation matrix. I used to, nowadays I don't. But I think the last term is sine theta 2, right? Then the term next to it is cosine theta 2 and sine theta 1 or theta 3, something like that. I don't remember what that is, but so what you do is, this rotation matrix that we obtained, which is 0R3, that has symbols. And on the right hand side, what we will do is, we will equate it to the numbers that we have. So this number is a 0.2, this number is a 0.1, etc., etc. And then what we will do is, we will do a term by term comparison and select those terms wisely. So I would say sine theta 2 is equal to 0.2. That gives me the value of theta 2. Then I would use this value and say cosine theta 2 sine theta 3 is equal to 0.1. Substitute this theta 2 value here and then get the value of theta 3. Are you with me so far? So what you need to do is, you need to select 3 terms, because we have to find out 3 equations and 3 unknowns. From those 3 equations, we have to find out 3 unknowns. Everyone understood this? Now, please understand, the trick here is, just like inverse kinematics for position, since these are trigonometric relationships, the same answer can be achieved in different quadrants. So just be mindful of that. So if you use MATLAB, and if you use a sine 2 or a tan 2 or a cos 2, MATLAB, yeah.
Where does that second matrix come from?
This second matrix on the right hand side, this comes because I give you that my end effector is at 20 degrees roll, 30-degree pitch, and 40-degree yaw. So what I do is, I use MATLAB or some other tool to represent this in the consistent frame. So basically, dollars to dollars, pesos to pesos. So roll, pitch, and yaw is given to you. You use the MATLAB command, say Euler to rot, and then that will give you a 3x3 matrix. That is the rotation matrix representation of the Euler angles. Question? Oh, wait. Because that's not easy. There are 12 combinations possible, so just hold your horses. Okay. Any other question?
We've been working in rotation matrix this entire time.
Do you want to work in Coutonians? That is more fun. Okay, good. So rotation matrices, they are easier to visualize, but Coutonians are more powerful. Okay. Any other question? So here is what happens at the end of the day. No matter what computer program you use, when it comes down to finding angles, at the end, it will convert that Coutonian into a rotation matrix and get the answers. So, any other questions? So this is very important. And I will solve the problem describing this technique maybe in next class. The next point which I want to emphasize is if you want to find out omega x, omega y, and omega z, these are the angular velocities. That goes without saying that omega x is about I naught, omega y is about j naught, and omega z is about k naught. And what you do is you have 0h1, you will calculate 0h2, and you will calculate 0h3. And then from 0h1, you would extract 0r1, multiply that by 0, 0, theta 1 dot, then 0r2, 0, 0, theta 2 dot, and then finally 0r3, and that will become 0, 0, theta 3 dot. So this entire expression finally can be expressed as some matrix multiplied by theta 1 dot, theta 2 dot, and theta 3 dot. Some of you may ask me how this jugglery happened. This jugglery happens because you are going to multiply 0r1, which is a 3 by 3 matrix, multiplied by so 3 rows, 1 column. So what you're gonna get, you will see that you will get 3 rows, 1 column. Again, you will get 3 rows, 1 column. Again, you get 3 rows, 1 column. It's better if I write this down. So this is a 3 by 3 matrix. Multiply this by 3 rows, 1 column. This is a 3 by 3 matrix. Multiply this by 3 rows, 1 column. 3 by 3 matrix. Multiply by 3 rows, 1 column. So as a result, you are gonna get 3 rows, 1 column. Here, you are gonna get 3 rows, 1 column. Here, and you are gonna get 3 rows, 1 column here. And what you can do is you can extract, so separate out theta 1s that is appearing here, theta 1 and theta 2 that is appearing there, and theta 3 1 and theta 1 and theta 3 2 and theta 3 appearing over there, and you can fully populate this matrix. And this matrix will be comprising of theta 1, theta 2, theta 3. There could be sines and cosines, and at the end you have these. So this is super important. This is called as, these are the joint velocities. And these are the end effector inertial velocities. And this matrix is called as Jacobian. And Jacobian is a fancy word for taking derivatives. So let me explain you what that is. Imagine that if I'm just going to give you an example. I have an expression. Let me start with px. So if I have an expression px is equal to, say, r cosine of theta. Okay, r cosine of, say, theta 1. And if I want to find out the velocity px dot, r is a constant, so that comes out of the derivative. Cosine is minus sine theta multiplied by, using the chain rule, derivative of theta 1. So I got this. Do you agree with me? So what this is, it is telling me a relationship. It is telling me the relationship between this angle and this linear displacement. And simple example is, say, if I have a robot, which is something like this. This is theta 1. So what I have here is I have minus r sine theta 1 multiplied by theta 1 dot, which is px dot. Now you may say, what is so great about it? Now here is the physical interpretation of this equation. Before I go to the Jacobian, this understanding is very important. Px dot is nothing but a very small change in px divided by a fixed time step that is equal to some quantity multiplied by small change in theta 1, something like this, divided by time. So I can say small change in px with respect to time, so I would just say delta t, and multiplied by small change in theta 1 with respect to some time. So this is what it is. So what I did, this derivative equation that we have been talking about and studying for a long time is nothing but a mathematical relationship between the change of variables. And the only variable here at this point is theta 1. Do you agree with me? Now imagine if I had two variables. Say for example, theta 1 and theta 2. What is the most natural way of explaining that change? The most natural way of explaining this change, say for an example, if px is function of theta 1 and theta 2, the total change in px, so I'm going to call this delta px, is going to be a quantity multiplied by small change in theta 1 plus another quantity multiplied by small change in theta 2. Do you agree with me? Delta t is constant. Delta t is, say, 1 for the time being. So now my px is dependent on one quantity multiplied by, so if you think about it, this is nothing but the slope multiplied by the change in the x value, and again slope multiplied by change in another x value or y value. So this geometrically can be represented something like this. See, this is px, this is theta 1, and this is theta 2. And this change in px is achieved because of changes in theta 1 and theta 2. So basically what you do is you have a change in the theta 1 direction and you have a change in theta 2 direction, and these individual changes contribute to the overall change of px. Everyone understood this? Now let me make this a little bit more complicated. Imagine if I have same thing with py. If I have same thing with py, then I can say something like this. So this is going to become theta 2. So now, if I were to take this A, B, C, and D, and then I formulate this like this, delta Px, delta Py is equal to A, B, C, and D. This A, B, C, D is nothing but the Jacobian. So Jacobian is nothing but relationship between the overall change to the changes to its individual components. Once again, Jacobian gives you the relationship between the overall change, the change of the individual components. Now, here is an example. You have $100.10. Okay, you have $100.10. If I give you $1 or if I give you 1 cent, you are gonna have, there will be some change. But now the question is your total change more dependent on the change in the dollar or change in the number of cents? Jacobian dictates that. So, which means if you know there is a change in a quantity, you want to find out of those two individual elements, which element is contributing more to the overall change. And that is what is the meaning of Jacobian. Yeah, question? Up?
When you mentioned that, so when you we have theta 1 dot theta 2 dot 3 dot is the z component. It's because the joints are always
correct. That is the reason why we use the sign convention where z is passing to the joint. Everything will come together. Don't worry.
what are these theta 1 theta 2
Theta 1, theta 2, theta 3 are the individual joint rotations, and theta 1 dot, theta 2 dot, and theta 3 dot are individual joint velocities.
end effector inertial angular velocity.
Yes, this is end effector inertial angular velocity. Everyone understood this? Any questions? Yeah.
So generally, our input is showing velocity, and we find out the Jacobian metric to calculate the end effector. Am I right?
Yes. So here is how it goes. You are given some joint velocities. Those joint velocities are changing with respect to time. So what you will do is you will take the snapshot of the joint velocity. You will take the snapshot of joint angles at that joint velocity and plug those values in and find out either your omega x, omega y, and omega z at that time. Does it make sense? So all this information is very, very important. And yeah.
So you said those equations are true when the angles are close to 0.
Very, very small.
So you mean the joint and theta 1 theta 2 theta 3 should be close to 0.
At each snapshot, if you are sampling the joint angle variation at 1000 hertz, then basically those joint variations are going to be very, very small. That's why those linearity assumption is applicable. Otherwise, the linearity assumption is not applicable. Actually, theta 1 is small, theta 2 is small, theta 3 is small, theta 1 dot is also small, theta 2 dot small, theta 3 dot small. Because if theta 2 dot is large, then maybe theta 1, theta 2, or theta 3 could be large. So the way that problem is solved in actual robots is if your joint values are very large, then you perform the discrete integration at a very high update rate. So you will do 100K, 10K, 30K, whatever. So you basically take the snapshot so that the teeny tiny change in that frame is small. Overall change may be big, but in that frame, that change is small. Yeah, go ahead.
Jacobian
Mhm.
calculator and theta are almost zero.
No, Jacobian you can calculate when thetas are changing. So Jacobian is a function of theta 1, theta 2, theta 3, theta 3, 4. I mean, theta 1, theta 2, and theta 3, right?
That was my doubt. Jacobian can be calculated when theta, but you said this equation operates only when theta.
So if you want to find the answer to that question, so let me take an example, and that would actually make things very clear. Let me take an example. Say for an example, if my values of theta 1 is 30 degrees, theta 2 is 40 degrees, theta 5 is 30 degrees, and my joint velocities, theta 1 dot is 2 degrees per second, theta 2 is 4 degrees per second, theta 3 is say 5 degrees per second. What I would do is I would find out the value of this Jacobian for these joint angles and then substitute these thetas over here and get the answer at that time. Because please understand, since theta 1, so theta 1 dot, theta 2 dot, and theta 3 dot, these are non-zero velocities. Clearly, theta 1 is going to change after 1 second. Theta 2 is going to change after 1 second. Theta 3 is going to change after 1 second. So basically, this equation is valid. These values are valid at that snapshot. That's what it means. And we'll solve the problem, actual problem at the time things will become clear.
So you said that if the iron is in the distal position, if robot has to move a larger distance, we take multiple snapshots. And so are we shifting the frame in each snapshot little by little to the final position?
Yes. So basically what you do is you take the snapshot, and so when these equations will not be valid if you decide to take, okay, here is the idea. If you decide to take the angle here and velocity here, that's not going to be valid. As long as your angle and velocities, those are in the same or one or next frame, that is actually, that works. And if you go to avionics, this frame matching is a very critical problem, because every system, and even for robotics, every system works at a different update rate. So if you want your robot, suppose a high-speed robot, to behave consistently, then you need to match the frames. You cannot take the velocity from one frame and take the angle from another frame and try to find the answer. That would make the robot unstable. So basically, they try to match the frames. And many a times, the sensor data that is coming at you may not come at the same frame. So you have to be sort of tolerant to that. So you have to use some type of error correction and make sure that you are getting this data in this consistent frame. Yeah.
How do we determine our joint velocities?
So joint velocities will be given to you. Or other way to do that is, imagine 3D printer. You are trying to 3D print something. So feed and speed is dictated by the application. So based on those feeds and speeds of the end effector, you will find your joint velocities. That's why your 3D printer stepper motor sometimes moves fast, sometimes moves slow. So basically, because you have some feeds and speeds that your application demands, and the joint angles or joint velocities are calculated to achieve that desired feeds and speeds are achieved. So you have to solve that inverse problem multiple times. Any other question before I go to next part?
Usually, what errors can cause the joint velocities and the proportionality with the inertial and effector.
So this is all good. What we talked about, this is all great in theory. Okay. In actual practical examples, what you do is you have an encoder that is attached to the motor. You have some type of a sensor that is monitoring the workpiece. And the data coming from the sensor, data coming from the encoder, which could be at different update rates. Sometimes there could be issues in data transmission. Sometimes encoder has high resolution. Sometimes the encoder has low resolution. Sometimes you get data dropouts. Sometimes these are all digital communications, which means you have zeros and ones coming through the digital line. Sometimes zeros and ones get mixed. So at that time, the frames, they don't match. So as a robotics engineer or a software engineer, you have to make sure that the data that is coming to you passes through some integrity checks before you actually take that data and process. So that actually causes mismatch. So, but that's a very common problem in robotics. But the basically operating systems or the robot operating systems, they have built-in checks to compensate for these data communication buses. Any other question? Okay. Now what I want to do is I want to give you basically the theoretical underpinning for Jacobian, and that is Taylor series. So Taylor series, remember Taylor series? So if you have a variable, I'm going to call this variable px. And if you are interested in this px depends upon one variable theta 1, then from Taylor series, delta px is equal to dpx divided by d theta 1 multiplied by change in theta 1. Do you agree with me? Remember Taylor series? If this px is dependent on px, which is theta 1, theta 2, delta px is, since theta 1 and theta 2, these are two independent variables, the derivative will not be full, it will be partial. Why partial? Because there are two independent variables. There are, so theta 1 and theta 2 are two independent variables. So this will become partial px divided by partial theta 1 multiplied by delta theta 1 plus partial px multiplied by partial theta 2 multiplied by delta theta 2. Do you agree with me? Everyone understood why is that? Because very simple quantity. So you have $100 10 cents. Again, remember this. If you have $100 10 cents, if I give you $1, your weight is going to be different if I were to give you 1 cent. Do you agree with me? So if I were to write down, I want to find out if I have $100 1 cent, and if I give you $1, then clearly this $1 carries more weight compared to 1 cent. So Jacobian essentially gives you the weight. Now, if I were to do the same thing for delta py, same logic, delta py divided by theta 1 plus delta py partial theta 2 delta theta 2. So what we did, we took the derivative in one dimension and expressed that as a derivative in two dimensions. There is something else that I want you to understand. We recognize that theta 1 and theta 2 are two independent variables. theta1 and theta2 are two independent variables. What is the geometric meaning of these two independent variables? Geometric meaning of these two independent variables means these two variables are geometrically perpendicular to each other. Because as soon as these variables are non-perpendicular to each other, then clearly one variable could influence the other variable. Everyone understood this? That's why we have theta1 that is independently influencing px, and theta2 which is independently influencing px. And that is the most important problem, because there are some coordinate frames that deliberately they are not orthonormal coordinate frames, which means the x and y's, rather than like this, they are like that. So in that particular case, the Jacobian will not give you a very clean solution just like that. So if I were to write this, this is going to become delta px, delta py. And to be honest with you, I'm not going to compute any of these Jacobians by hand. We will use MATLAB. But I want you to understand what it signifies mathematically. Partial px, partial theta1, partial px, partial theta2, partial py, partial theta x, theta1, partial py, partial theta2. And in case if you are wondering how this came about, so remember this trick. This guy is here. This guy is here. This guy is here. And same thing, this guy is here. That is how you have to remember the Jacobian. And Jacobian you will see in lot of mechanics applications. And what I will do is I will stop here, but in next class, I will actually take an example. That example is the Sphera robot, and we will go from start to end, and I will show you how we can solve the entire robotics forward and inverse kinematics problems, including the velocity analysis, just using MATLAB. Some students ask me, can we simulate it? Can we visualize it? It's super simple. Go to Sim Mechanics, which is the MATLAB toolbox. And if you go to Sim Mechanics, you will be able to construct the robots just by dragging the blocks. Alternate option for that is, if you have SolidWorks, create the solid model. MATLAB will import that solid model into Sim Mechanics and create the joint structure, the robot assembly for you inside MATLAB. So just if you guys want to play with it, I'm gonna stop here and we will continue the discussion next time.